Welcome back to Hypnosphere. This is a calm place for unhurried science. A soft track through ideas that are big enough to feel like weather inside the mind and gentle enough to ease you toward rest. If it feels right, let me know where you are listening from tonight and what time it is for you. I like imagining those quiet lights, kitchen windows, and bedside lamps, mountain cabins, and city balconies, a scattered constellation of listeners who share a slow curiosity. Tonight we will explore the science behind a phrase that has floated into poetry and popular culture: the butterfly effect. You might have heard it as a sentence that sounds almost like a riddle. A butterfly flaps its wings in Brazil and sets a tornado in Texas. It is a vivid image. It turns smallness into possibility, and it turns weather into a story that travels on the back of a tiny motion. But what does it really mean? And what does science say when it sets the poetry down and begins to measure? The short answer is that the butterfly effect is a property of certain systems, including our atmosphere, where tiny differences in starting conditions grow with time into large differences in outcomes. The long answer is richer and kinder. It is not a claim that butterflies are somehow responsible for disasters. It is not a claim that every small thing triggers a giant event. It is a statement about sensitivity, about how nonlinearity folds and stretches the space of possibilities, and about how predictability has a horizon that you cannot push back by will alone. To begin, it helps to sit with something ordinary. Imagine a pot of water on a stove just before it boils. The surface looks calm. Then, without warning, a small shimmer glides across, and another, and very quickly, the whole pot is alive with rolling cells. You could tap the side of the pot and say that your tap caused the boil, but you would know that the truth is more subtle. The water was near a threshold. Small disturbances ride on top of that state, and they can be amplified by the conditions that are already present. That is how chaos begins in many settings. Not with an arbitrary magic spark, but with a system that is already poised to respond. Weather is like that pot, though far more complicated and beautiful. The equations that describe air and moisture and heat are nonlinear, which means their outputs do not simply add. When two waves meet, they do not always pass through each other unchanged. They can merge into larger shapes. When wind passes over a mountain range, it does not just slow down. It sheds eddies and rotor clouds, spirals of air that curl and break and reform. Small changes in temperature, humidity, or wind speed can alter the future shape of those patterns in ways that grow with time. When scientists speak of the butterfly effect, they are thinking of sensitive dependence on initial conditions. That phrase is longer, and it sounds technical, but its heart is simple. If you start two versions of the same system with conditions that differ by an amount too small to notice, you can still end up with very different outcomes after enough time has passed. Imagine rolling two marbles down a ridge. If both begin perfectly, they follow the same side. If one begins a paper width to the left, it picks the other valley. The set of possibilities has been divided by a thin line. In many chaotic systems, the ridge is everywhere, woven through the space of options like a fine lace. It is important to remember that sensitive does not mean uncaused. Chaotic does not mean random. These systems are deterministic. If you could specify every starting detail with infinite precision, the future would follow with no surprises. The problem is that no one can specify anything with infinite precision, not even the position and speed of two marbles on a ridge of wood, and certainly not the temperature and pressure at every point in the sky above an ocean. The butterfly effect is the recognition that even the modern story of the butterfly effect begins with weather, but its roots reach back to a mathematician studying the heavens. In the late 19th century, Henry Poincare was asked to solve a prize problem about the motion of three bodies under gravity. The two-body problem, like Earth and Sun, yields graceful ellipses. The three-body problem, like Sun, Earth, and Moon, is far less polite. Poincare found that small changes in starting positions and velocities can grow into large differences over time. He saw that curves in the space of possibilities can fold, making motion sensitive in a way that simple periodic systems are not. He did not have a computer. He had insight, and he drew a new map of dynamics that showed islands of stability and seas of complex motion side by side. Decades later, in the early 1960s, Edward Lorenz was working as a meteorologist at MIT. He had built a small weather model with a handful of equations that represented convection, the rising and sinking of air as it gains and loses heat. His computer printed numbers on long sheets of paper. One winter day, Lorenz wanted to repeat a run and watch a section more closely, so he typed in the numbers from the printout as new starting values. The machine hummed and chattered its way forward. At first, the new run matched the old one. Then it began to drift. The match disappeared. The second run wandered into a different pattern. The cause was humbly small. The printed numbers had 3 decimal places. The computer stored 6. Lorenz had restarted the model with a rounding error in the 4th decimal place. That tiny difference had grown with time until the new path bore no resemblance to the original. He at first suspected a hardware fault. He checked the vacuum tubes. He checked the wiring. In time, he realized that the fault was in the nature of the equations. His model was deterministic. The same inputs always gave the same outputs. But the future depended so sensitively on the precise values of those inputs that any small disturbance, any measurement noise, would make the future diverge. Lorenz gave a talk with a memorable title, Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? He did not mean that specific butterflies steer storms like tiny pilots. He meant that the atmosphere is a system where microscopic differences can grow, and that this growth limits how far into the future one can predict the detailed state of the weather. He introduced a new shape into science, the Lorenz attractor. If you plot the evolving state of his simplified model in a 3-dimensional space, the path loops around 2 lobes, crossing near the center and then being flung to the other side. The path never intersects itself. It never settles into a simple loop, yet it stays within a bounded region. The shape has a structure that repeats its smaller and smaller scales, like a leaf with veins that sprouts smaller veins that sprout smaller ones still. Imagine the attractor as a sculpture made of thin wires. The future of the system flows along the wires, never leaving the sculpture, but never tracing the same wire twice. The wires come close, so close that two nearby points are almost indistinguishable. And then the paths depart, one heading left and one heading right, not because of a coin toss, but because that is how the flow lifts off those wires in that region. If you are a weather forecaster, those thin separations are your anxiety and your art. You have to know where the wires pack tightly and where they fan out. You have to represent the range of possible futures rather than a single line. The word nonlinearity matters here. In a linear system, if you double the input, you double the output. In a nonlinear system, doubling the input might triple the output or cut it in half, depending on where you are in the state space. The atmosphere is full of nonlinear processes. Cloud droplets form only when the humidity crosses a threshold, then grow rapidly as water condenses. Winds strengthen when temperature gradients sharpen, but those winds also stir and mix, softening the gradients that feed them. Each process feeds back on the others. Think of a microphone placed too close to a speaker. A tiny noise is captured, amplified, fed back, and becomes a howl. The physics is simple. The consequence is dramatic. In weather, the feedbacks include latent heat from condensation, radiation to space, and friction with the surface of the Earth. Sensitive dependence is not only about air and water. You can hold chaos in your hands. Take a double pendulum, a rod hanging from a pivot with a second rod hanging from its end. Set it swinging gently, and it moves like you expect, a soft sway. Nudge it a little harder, and the lower arm begins to cartwheel unpredictably. Two nearly identical starts quickly diverge, the tips tracing intricate patterns in the air. The equations are deterministic, but the smallest difference in the starting angles or speeds leads to different sequences of tumbles. Watch long enough, and you see a kind of personality in the motion, not a repeat, but a flavor. There are other quiet examples. A narrow stream rippling over shallow stones. Tiny adjustments in the flow make eddies appear, then merge, then break. A candle flame lifted by a draft, wobbling, then steadying as the air changes. Grains of sand sliding from the crest of a small pile. Most grains resting, while a few cascade in a miniature avalanche, the pile never settling into one final shape. These are not the dramatic failings of control. They are ordinary states of matter at work, continually adjusting to the energy that passes through them, finding patterns that are stable enough to persist while still being alive to tiny changes. In the years after Lorenz, researchers began to look for fractal structures in dynamics, patterns that repeat at different scales. The coastline of a rocky bay looks rough from far away. Walk closer, and you see the same jaggedness in smaller inlets and crevices. Zoom in again and again, and the pattern persists. That persistence is a signature of processes that lack a single natural scale, and chaotic systems often. To understand chaos gently, it helps to change how we picture motion. Instead of plotting variables against time, we can plot variables against one another. This creates a space of states, often called phase space. A pendulum is a point in a two-dimensional phase space, with one axis for angle and 1 for angular speed. As the pendulum swings, the point traces a loop. For a pendulum without friction, the loops nest smoothly. Add friction and the loops spiral inward, ending at the point that represents rest. That point is an attractor. It is a place in the space of possibilities that collects trajectories. Now imagine a system where there is no single resting point and no simple loop, but there is still a region where the motion always remains. The Lorenz attractor is like that. It is not a point. It is not a closed curve. It is a tangled set of pathways, layered and folded into 2 loose wings. The flow in that region stretches trajectories apart and then folds them back, like kneading dough. Stretching creates sensitivity. Folding keeps the motion bounded. Together they create structure that never repeats and never drifts away. How fast do nearby paths separate? That is where a Lyapunov exponent enters. If 2 trajectories start a microscopic distance apart, their separation will grow for a while, roughly like a small exponential. The exponent measures the rate of growth. If the exponent is positive, the system is chaotic. If it is 0 or negative, differences do not grow, and the system is not sensitive in that way. You do not have to derive the equations to feel the meaning. Think of 2 leaves in a stream that begin side by side. If the current is laminar, smooth and steady, they stay near each other. If the current is full of eddies, their paths diverge. The Lyapunov exponent is a way to measure the average strength of those eddies in the space of states. There is a friendlier example that lives purely on paper and in simple computer codes. The logistic map. It is a formula that takes a number between 0 and 1 and returns another number between 0 and 1. Then you feed the output back as the next input. As you do this over and over, the sequence of numbers reveals the behavior. For small parameter values, the sequence settles to a fixed point. Increase the parameter, and it settles into a 2-step cycle, then a 4-step, then an 8-step. This is called period doubling. Push further, and the behavior becomes chaotic, with a dense mix of values that never repeat. Yet even in the chaos, there are windows where order returns, islands where the system briefly finds a rhythm before losing it again. Mitch Feigenbaum discovered that the parameter values at which these doublings occur approach each other in a regular way. The ratio of the distances between them settles to a constant number, about 4.669. This constant appears in many systems that undergo period, doubling en route to chaos. You do not have to memorize the number. What matters is the idea that chaos is not the absence of structure. It is a different kind of structure, one that includes universality. Different systems, from dripping faucets to electronic circuits, can share the same pathways from order into chaos. Another simple picture comes from a driven damped pendulum, a pendulum with friction that is also being nudged periodically. For some settings, it settles into a steady beat, its motion locked to the driving rhythm. Change the driving strength or frequency slightly, and the motion can bifurcate into more complex patterns. Change it a little more, and chaotic swings appear, or tiny differences in the angle at which you release it lead to large changes in later swings. Paint a plot of where the pendulum crosses a particular angle each time it is pushed, and a delicate fractal pattern emerges. The boundaries between different long-term outcomes are riddled with filaments. This riddling is the geometric face of sensitive dependence. None of this is outside the ordinary world. Laser pointers can display chaos in their light intensity when pushed and cooled in particular ways. Electrical circuits with a few components can show chaotic oscillations. Heart tissue, under stress, can slip from a healthy variability into rhythms that are too irregular. A dangerous chaos that cardiologists watch for. Ecosystems can hover near thresholds, or small changes in population, food supply, or temperature can flip the community into a different balance. Understanding that such thresholds exist allows care. It invites buffer zones and gentle controls rather than constant hard pushes. In weather and climate, these ideas become practical. Weather is the day-to-day path on a complicated attractor, sensitive and alive. Climate is the shape of the attractor itself. Change the composition of the atmosphere by adding greenhouse gases, and you change the energy balance of the system. That alters the attractor. You have not nudged the system from one spot to another within the same shape. You have changed the shape. This is why the butterfly effect is not a clever excuse to shrug at climate change. Chaos limits detailed prediction at a point in time. It does not erase the response of the system to sustain changes in its boundary conditions and energy sources. Forecasting in the presence of chaos uses ensembles. Imagine releasing many tiny balloons into the atmosphere at once, each carrying the best estimate of the current state, plus a small random jitter in temperature or wind. Let each balloon drift forward according to the same laws. After a day, the balloons will spread. After 3 days, they will spread more. The cloud of balloons shows the uncertainty in our knowledge of the future. It is a picture of sensitivity in action. From that cloud, you can extract probabilities. 40% of the balloons end up in a rainy region. 60% do not. That becomes the forecast you see. There is a hidden craft in creating those initial small jitters. They must represent not just any random noise, but the kinds of errors our instruments and models make. Data assimilation is the discipline that merges observations from satellites, aircraft, ships, and stations into a coherent picture of the present. It accounts for the biases of each instrument and the physics that connects variables. It balances the pull of new data against the inertia of the model. This is how an abstract concept from chaos becomes a daily practice. It is patient and incremental. It has lifted our forecast skill in a way that respects the horizon set by sensitivity. It is also worth speaking to a common feeling. Chaos can sound like the world is uncontrollable. Yet there is a field known as control of chaos that shows another side. Many chaotic systems can be guided gently by small, well-timed inputs. You do not force the system to obey. You nudge it into a nearby stable orbit that already exists inside the tangled attractor. This is done in laboratory lasers and in mechanical systems. The trick is to measure where you are with enough care to know which small tap will move you toward the stable region. It is a partnership between sensitivity and feedback. In this way, chaos is not a failure of order. It is a landscape in which many small paths can be found that keep you near where you want to be. As we let these images settle, one question invites us onward. If chaos is everywhere, why do so many things look stable? Planets circle the sun for billions of years. They trade, winds blow. The heart keeps its beat. The answer is that many systems are only partly chaotic, and the parts matter. The solar system has pockets of chaos in the asteroid belt and among small bodies, yet the major planets follow predictable paths because conservation laws and resonances provide stability. The atmosphere is chaotic in detail, yet global circulation patterns persist because the planet is heated more at the equator than at the poles, and spins in a way that shapes the flow. The presence of chaos does not erase structure. It coexists with it. In the next part, we will try on some analogies that make these ideas gentler still. We will walk along a coastline and see fractals with our feet. We will ride a river and feel how meanders and eddies teach us about attractors and transitions. We will look up at the clouds and read their edges. We will step back to look at life and choices. Imagine flying slowly above a river on a clear day. The water is brown-green, braided with lighter streaks of foam. Where the current is straight, the surface looks smooth, a sheen with tiny capillary ripples. Where the river curves, the outer bank digs deeper and faster, carving a cut bank. The inner bank becomes a beach. Over years, the river shifts its bends, sweeping into an S that migrates across the valley. Every bend is a kind of attractor, a shape the flow wants to trace, but within that shape, the motion is alive. A leaf tossed near the surface can swirl into an eddy and then slip back into the main current. Two leaves, dropped a moment apart at the same place, can diverge and rejoin, or diverge and never meet again. This is chaos without menace. It is simply the character of flowing water. Now walk along a rocky coast. From far away, the shore looks like a line with a few bays. Up close, the line becomes a lace of waves and rock pools and rough projections that jut into the sea. Closer still, the edges of individual stones are jagged. The shape you see repeats at different scales. That is what a fractal is, not a perfect repetition like a pattern stamped by a machine, but a statistical similarity across scales, born of the same forces acting again and again. Wave action carves rock with a rhythm of impact and retreat. Soft layers erode first. Harder layers stand longer. Given time, the coastline writes its own signature, and that signature has no single scale. Clouds have this quality too. A cloud's edge is rough. From a plane, you see smaller billows on top of larger ones. From the ground, you see wisps riding on larger decks. The physics is convection, the rising of warm moist air and its cooling and condensing, repeated in many sizes at once. These images help because they suggest that chaos is not a high drama reserved for special events. It is a background presence in many natural processes. It explains why a fire can spread in irregular fingers. Finding wind can fuel in patterns that are themselves irregular. It explains why populations of insects can boom and crash when a small change in weather or predation pushes them past a threshold. It explains why a heart under stress can click into arrhythmia, with a normal attractor that represents a healthy loop in phase space gives way to a different attractor that is unstable, sending the beat wandering. In each case, sensitive dependence lives inside a broader structure, and understanding that broader structure gives ways to anticipate, guide, or recover. Consider the solar system, a quiet clock when sketched in a textbook, a network of subtle resonances in reality. The major planets hold stable patterns over very long periods, in part because their mutual tugs average out and because their masses and distances create margins of safety. Yet within this clock, small bodies feel chaos keenly. An asteroid near a resonance with Jupiter can be nudged into an orbit that shifts from circular to elongated to crossing paths with other bodies. The exact future is sensitive. The statistics are not. There are regions of space where asteroids do not linger because chaotic paths shepherd them elsewhere. Even here, chaos shapes a landscape without erasing predictability entirely. In climate, a gentle distinction matters. Weather is an initial condition problem. Small errors in the present grow into larger disagreements about tomorrow. Climate is a boundary condition problem. Change the energy that enters or leaves the system, or the substances that control how energy is trapped, and you shift the average state around which the weather dances. Greenhouse gases increase the insulating quality of the atmosphere. The attractor that represents the climate shifts toward warmer temperatures, different precipitation patterns, and altered extremes. Within that attractor, daily weather remains chaotic, but the statistics change. The dice are loaded differently. Here the butterfly effect is not the right metaphor. A better one is the dial on the stove. Turn it, and the pot you saw earlier reaches boiling sooner and more often. Tiny taps on the side still matter for the exact path of bubbles, but the background has shifted. It is worth visiting two more ideas that can sound technical, but feel simple when you hold them just right. The first is synchronization. Two chaotic systems can sometimes be coupled so that their unpredictable motions lock together. This has been shown in lasers and in electronic circuits. The second is control of chaos, which we touched on earlier. In the OGY method, named after OTT, Grebogi, and York, you measure where you are in a chaotic system and apply tiny adjustments to steer it toward a stable periodic orbit embedded inside the chaos. Think of it like walking a path in fog using a faint fence that you can touch now and then. These ideas teach us that sensitivity is not just a barrier, it is also a resource. Because the system responds strongly to small inputs, you can influence it with gentle nudges if you time them well. Now return to Lorenz and to that famous question about butterflies. The image is so strong that it can pull us into a literal reading, so it helps to be precise and kind. A single butterfly is not responsible for a tornado. A tornado is the result of many interacting processes that span scales from tiny cloud droplets to vast air masses. The butterfly effect says that if you rerun a faithful model of the atmosphere twice, once with the butterfly and once without, the timing and path of small features may diverge quickly. After enough time, one run might contain a tornado in a region and the other might not, even though both runs reflect the same large-scale climate. That is sensitive dependence. It respects the complexity of causes. It does not say that any one small action creates or prevents a distant event on its own. Causes braid together across scales. It is comforting to remember that sensitive systems often have robust features. Ocean gyres swirl in the same basins, whether or not a small gust moves a leaf today. The Hadley cells, those great tropical overturning loops of air, exist because the sun heats the equator more than the poles and because Earth rotates. That structure persists while storms travel inside it unpredictably. In our lives, there is a similar balance. You cannot forecast every detail a week from now. You can shape the climate of your days. You can set boundary conditions that favor calm. A regular time for sleep. A walk in the afternoon light. A pattern of checking the weather once each morning rather than every hour. These choices change the attractor in which your smaller decisions wander. One more analogy before we turn toward closure. Picture a pinball machine. The ball moves under gravity and springs from bumpers that transfer momentum in ways that depend on exactly where it hits. A difference of a millimeter at one collision can send the ball on a completely different tour of the table. That is sensitive dependence written in steel. And yet the outcomes are not wholly mysterious. You can say where the ball spends more time. You can adjust the angle of the table and change the average behavior. You can design bumpers in certain patterns and know how they will shape the overall flow. Chaos lives inside a geography of influence. In this quiet space, the science starts to sound like advice without becoming moral. Pay attention to feedback. Notice thresholds. Respect horizons of predictability. Shape boundary conditions gently. Accept that uncertainty is not a failure, but a feature. And enjoy the beauty that appears when you let go of the need for exactity while holding tightly to the possibility of understanding. In the last part of our journey, we will bring all of this back to your daily life. We will talk about how to make decisions with ensembles in mind, how to be a good steward of your inner climate so that the butterfly effect can leave you with two very different feelings. One is a flutter of worry. If small things matter so much, then how can I be sure of anything? The other is a deepening calm. If small things matter so much, then I am free to act gently, to value modest habits, to trust that change accumulates. The science supports the calm. Sensitivity imposes a horizon on detailed prediction, but it also grants a way to shape patterns by attending to boundary conditions and feedback. You do not need to forecast every gust to set your sails wisely. Think of your day as a small dynamical system. It has inputs and outputs. It has feedback loops. It has attractors, those patterns you return to without thinking, like your morning routine, your way of handling a difficult email, or the path you take on an evening walk. If you want your day to be steadier, you can alter its boundary conditions. Sleep a little more. Place your phone outside the bedroom. Prepare a glass of water for the morning. These are not superstitions. They are small changes to the energy and information that move through your system. Over time, they shift the attractor of your days, so that even when the weather of life is chaotic, the average state is kinder. Decision-making can borrow directly from ensemble forecasting. When you face a choice with uncertain outcomes, imagine a handful of plausible futures. Not infinite, just a few. Let them diverge in your mind. What are the common elements across these futures? Those common elements are robust. They are like the features of climate that stay while the daily weather varies. You can plan around them. Then notice which futures are very sensitive to small changes. That shows you where to place your attention. A single conversation held sooner. A small buffer of time in your calendar. A contingency you can prepare with little cost. This is not control for control's sake. It is a way to dance with uncertainty without fear. On a larger scale, the science of chaos offers a posture for public life. In systems like public health or finance or ecology, small shocks can cascade when the system is poised near a threshold. That suggests building buffers, designing with redundancy, and avoiding brittle configurations that depend on everything going right. It suggests measuring the present with care, the way meteorologists do, because the quality of your initial conditions matters. It suggests humility, the willingness to update forecasts with new data and to present probabilities rather than certainties. This humility is not weakness. It is respect for the way the world works at its edges. There is a spiritual comfort, too, in realizing that randomness is not required to produce mystery. The world can be lawful all the way down and still surprise you. Deterministic chaos carries both qualities at once. The laws apply. The details wander. You can rest in that paradox. You can look at a cloud and enjoy its edges without asking for an equation to trace them. You can look at the looping path of a moth around a porch light and see not aimlessness, but a trajectory in a flow field, pulled by scents and breezes and the warmth of the bulb, sensitive and alive. The butterfly effect also asks us to be gentler with stories of cause. We often want a single reason, a clean line from event to consequence. Chaos teaches that causes braid. A storm is the result of 1,000 small pushes and pulls within the frame set by the season and the sea. A decision at work unfolds inside the climate of the team, the incentives that guide it, the sleep that its members have had, and the weather of the day. When you tell the story afterward, tell it with generosity. Give credit to the boundary conditions that made success more likely. Acknowledge the sensitivity that could have spun the day another way. This way of telling makes room for gratitude and for responsibility at the same time. And what of the original butterfly? It still flaps, but now it feels less like a myth and more like a reminder. There are many scales in the world. At each scale, patterns form. A butterfly shapes the air around it. 1,000 butterflies shape a meadow. The meadow shapes the ground and the moisture. The season shapes the region. The climate shapes the planet. At each step, small actions gather and feed into larger flows. We live in those flows. We add our own small motions. We do not control the river, but we influence our reach of it. From a distance, the science of chaos can seem like a source of unease. Up close, it is a kind of kindness. It invites patience with what cannot be pinned down. It rewards attention to what can be shaped. It explains why your weather app sometimes changes its mind, and why that is not a failure, but a reflection of a deep truth about air and water. It explains why pundits who speak in absolutes about complex systems are often less reliable than those who offer ranges. It explains why the heart, when healthy, does not beat like a metronome, but with a living variability. As we close, feel free to let the details drift and keep the sense of it. Sensitive dependence is not a threat. It is a feature of many beautiful systems. It gives forests their patchwork. It gives clouds their edges. It gives us a reason to care for small habits and to design our lives for resilience. If you are moving towards sleep, let that thought hold you. If you are moving into your day, let it shape your plans gently. Thank you for spending this time in the hypnosphere. If you enjoyed this calm journey through the science of the butterfly effect, you are warmly invited to subscribe. There is always room here for another quiet exploration, another evening or morning of wonder, another slow breath shared under the same sky.